Welcome to The Explainer. Today, we are jumping right into two huge concepts in C# concurrency, the old school thread versus the new school task. Look, if you want to build apps that are fast and don't lock up, you absolutely have to know the difference here.
All right, let's just get right to the heart of it. The problem every single one of us has faced, right? You click a button in your app. It needs to go fetch a big file or crunch some numbers, and bam, the whole thing just freezes up. The user is just staring at a spinning wheel. The secret to fixing that? It's all about getting your code to do more than one thing at once. Okay, but before we go any further, we gotta clear something up. Two words that get thrown around and mixed up all the time: concurrency and parallelism. Think of it like this. Concurrency is like one amazing chef juggling a bunch of pans on one stove. They're all cooking, progress is being made on all of them, but only one is getting direct heat at any given instant. Parallelism? That's having a whole team of chefs, each with their own stove. They are literally all cooking at the exact same time. It's a subtle but super important difference. So how do we pull this off in C#? Well, the framework basically hands us two main tools for the job. And really getting the philosophy behind each one, that's the key to writing code that's not just functional, but truly efficient. First up, we've got the OG, the original workhorse, the thread. Now, a thread is the real deal. It's the most basic thing the operating system itself knows how to run. When you spin up a new thread, you're basically picking up a direct line to the OS and saying, hey, run this for me. It gives you raw, fine-grained control over exactly what's happening. Then you've got its slick modern cousin, the task. A task is totally different. It's a higher level idea. It's not the worker itself. It's more like the job description. It represents a piece of work that needs to get done, eventually. It's a promise that you'll get a result back later, and it lets the system figure out the messy details of which thread actually does the work. Okay, so we've got the low-level powerhouse and the high-level smart abstraction. So, when do you use which one? Let's throw them in the ring and see how they stack up. And this slide right here really nails the core difference. The rule of thumb is pretty simple. You only grab a thread when you absolutely need that down-to-the-metal control. Like, you need to tell the operating system, this job is more important than anything else, give it priority. For pretty much everything else you'll do day to day, especially with modern async await code, task is going to be your best friend. I mean, just look at the code. The difference in simplicity is staring you right in the face. With a thread, it's a two-step dance. You create it, then you start it. But task run, it's just one clean, beautiful line of code. And that's not an accident. This was all part of a huge effort called the Task Parallel Library, designed specifically to make this complicated stuff way easier for all of us. All right, enough theory. Let's get practical and see how this actually works. We're going to do a little rapid-fire Q&A and tackle some of the most common questions people have when they start using these. First question, and it's a big one. Your code needs to just wait for a second. So what do? Do you use Thread.Sleep or Task.Delay? It seems like a small choice, but believe me, the answer can have a huge impact on whether your app feels snappy or sluggish. Okay, here's the absolute killer difference. Thread.Sleep is what we call a blocking call. It basically puts the thread into a coma. That thread does nothing, it sees nothing, it's completely useless until the timer is up. And if that's your main UI thread, yep, your entire application freezes solid. Task.Delay, though, is the complete opposite. It's non-blocking. It politely tells the system, hey, I don't need this thread for a moment. You can use it for something else. Just wake me up when it's time. The thread is freed up to go do other useful work. It's a game changer for responsiveness. Right, so we said a task is a job description, not the worker. That begs the question then, who is actually doing the work? Where do these threads come from? Because they don't just appear out of thin air. The magic behind tasks is something called the ThreadPool. Seriously, think of it as a super efficient temp agency for threads. Creating a new thread from scratch is actually a pretty expensive operation for the OS. So instead of hiring and firing a new worker for every tiny job, the ThreadPool keeps a whole crew of threads on standby, ready to go. When you run a task, it just grabs a free thread from the pool, gets the job done, and then that thread goes right back into the pool, waiting for the next assignment. It's way, way more efficient. Okay, next question. What about when things go wrong? Error handling. Normally, if an exception isn't caught, your whole app can come crashing down. But what happens when an error pops up inside a task that's running off in the background somewhere? Does it just silently fail?
Nope. And this is another really elegant part of how tasks work. If an exception happens inside a task, the system is smart enough to catch it and just tuck it away inside the task object for safekeeping. The exception doesn't go anywhere until you actually try to get the result of the task, usually with an await. Then it gets rethrown right where you can see it, so you can wrap it in a normal try-catch block and handle it like any other error. It's super clean.
All right, how about cancellation? This is a huge one. Let's say the user starts a big file download, but then changes their mind and hits the cancel button. How do you actually, tell that background operation to stop what it's doing without just killing it brutally?
The modern way to do this with tasks is through something called a cancellation token. It's a really smart cooperative system. You pass this little token object into your method, and then inside your code, you just check it every now and then to see if anyone has requested cancellation. It's like politely tapping the worker on the shoulder and saying, hey, we don't need this anymore, you can stop. This is so much safer than the old, dangerous Thread.Abort method, which was like a sledgehammer that would just kill the thread instantly, even if it was in the middle of writing to a file or something, potentially leaving your whole app in a mess.
So let's recap. Tasks are generally safer, they're more efficient, they're easier to work with, which really leads to the million-dollar question, doesn't it? Is there any reason to even use the thread class anymore?
I mean, really, with all of this going for tasks, can't we just declare thread obsolete? Just use task for everything and never look back. And the answer is a hard no. Absolutely not. And here's why. Because a task is an abstraction. It deliberately hides the nitty-gritty details of the thread from you. But sometimes, in very rare, very specific situations, you need those details. You might need to set a thread's priority to high or manage its apartment state for calm interrupt. Weird, low-level stuff. And for those moments, task won't cut it. You have to reach for the thread class. It's still an essential tool.
Okay, so let's wrap this up with the big takeaway. For 99% of what you do, all your typical async and parallel work, Task is your hero. It's efficient, it's safe, it handles all the messy thread management for you. But you've got to keep Thread in your back pocket for that 1% of the time. For those moments when you need to get your hands dirty and have precise, low-level control, it's the only tool for the job.
And that brings us to one final thought to leave you with. The jump from thread to task was a massive step forward. It made something incredibly complex so much more manageable. But technology never stands still, right? As our apps get even more distributed and more complex, you have to wonder, what comes after task? What's the next big idea that's going to revolutionize how we write concurrent code?